So remember I said problem 4 on the final would have something to do with what we're going to talk about today? Here you go. This is the beginning of that. So think about this idea where I have a long, thin rod. We're not talking about, anything like this that has a big cross-sectional area on it. We're talking about something, a rod that might be long and thin like this. So when we change its temperature and it wants to expand or contract, it only does so along its length. If it had a big cross-sectional area and I heated it up, not only would it stretch this way, but it would also potentially expand outward in a volumetric way, or perhaps a area expansion. We'll talk about that more. But for this example, just think long, thin rod. So it has very little cross-sectional area. Is everybody confused about that? So here we go. If I start with some temperature T0, that's my beginning temperature. So my long, thin rod is sitting on the table. What's its starting temperature? Room temperature, roughly 70, 72 degrees, depending on what they have the thermostat set on, right? And if I were to add energy to this and cause its temperature to change, this thing would expand along its length. And that's what they're trying to show you here. Start at some temperature, somehow the temperature changes. It could be, this implies the temperature is increasing or decreasing?
Increasing.
Increasing. We typically, things expand when they heat up. Okay. So temperature plus some change leads to a delta L, a change in the length of the object. Okay. And there's you'll see these things over here. And let's write a laundry list. So basically it says the change in length of my long, thin object. Does anybody know what this thing means?
Alpha.
It is the Greek letter alpha, but in this case it means proportional to. Proportional to. So what this is telling you is that the change in the length of the object depends on the length I start with. So if I start with a 1 meter long thin rod and I heat it up by 100 degrees Celsius, it'll stretch. If I start with a 2 meter rod and I heat it up by 100 degrees Celsius, it'll stretch twice as far. The amount that it changes depends on the length we start with. This is what you're being told here. That's one thing that influences how much an object will stretch or shrink, for that matter. All right? And of course, it also depends on the change in temperature. So if I want to write, though, a complete equation, and this is what you'll need to know for sure, I take alpha, which is not the proportionality constant, unfortunately, don't get confused, times L naught times the change in temperature. So there are 3 things that influence how much a long thin rod will stretch or shrink. This depends on the type of material. So if it's aluminum, it will stretch differently than brass. You guys okay with that idea? Different metals or materials will stretch or shrink differently. Get everything else being the same. It depends on the material. This is, as I've said, the original length. and let's not be confused, this is T final minus T initial. Delta T, remember delta anything is always final minus initial. Final minus initial. So think about this. If I heat up my object, this delta will be
Larger than the original.
larger, so it'll be positive, good. And if I cool it down, this change will be negative, and I can expect delta L to be negative. It would shrink. Yes, Devin?
Does alpha mean a ratio or
Yeah,
constant?
it's not this alpha. So let me show you a chart of alphas, okay? Notice here it says alpha, the units are 1 over degrees Celsius or centigrade. So I've got, just looking at units, I've got 1 over C. What are the units of length typically? Meters. And my temperature could easily be in what, degrees Celsius, right? So Celsius final minus Celsius original. So what happens to the degrees Celsius? They'll cancel, and I'm left with meters equals meters. So the change in length equals, in terms of meters, equals the meters that come from the original length, at least the units. Okay. Let's take a look at that chart. All right, so where are we looking? We're looking here. This is the linear coefficient of expansion, alpha. And let's take a look at some different types of materials. So you'll see aluminum, this is 23 times 10 to the negative 6, but focus, these are all 10 to the negative 6. Focus on these numbers here, okay? So based on these numbers, just in this piece of the chart, which one will stretch the most given any kind of temperature change?
Lead.
Lead. It's the biggest alpha. So if alpha is biggest here, right, for the same starting length and the same change in temperature, we get the biggest change in length for lead. Aluminum is the next one, the next stretchiest one, so to speak. Which one is least stretchiest?
Quartz.
Quartz. So if I warm up quartz by adding energy to the system, I'll only get a fairly small change in length. Is that making sense to everyone? Okay, questions?
Why is it that